Okay, to do this problem, you need to determine if you need a free body diagram or not. You do it exactly the same way that you do all the other problems. It's not a dead giveaway, and so I need to count the degree of freedom. In this particular case, point A is moving. I'm told that. But if you hold A fixed, then and then ask yourself, can anything move and not fall apart or break or bend? And the answer is no, nothing else can move. B can't flip up off of this, or else B is not on the incline. So no, nothing else can move, so it's 1 degree of freedom. Whoops. So it is 1 degree of freedom. That means if you're given one velocity, you can find any velocities. I am given one velocity, and because it's 1 degree of freedom and one velocity given, that means I can find any velocity I want, and I don't need a free body diagram. Okay, I'm going to use the special points technique. To do the special points, you want to count how many bodies there are, and there's clearly at least one, the link. I am not going to count the rollers because they really are not doing much, because the edge of the link is simply moving up and down A, and it's moving along this incline at B. So the rollers really aren't doing much, so I'm not going to count them. So I have one body. Now look at the special points. There's 3 reasons why points are special. A is obviously special for a couple of reasons. One, it's touching more than one body. It's touching the link, and it's touching the vertical wall. It's also, I know what it's doing, so there's 2 reasons it's special. B is special because, again, it's touching more than one body, and I want to know something about it. It only needs to have one reason to be special, but anyway, in this case, there's 2 special points. The next thing to do is to make sure you set up a coordinate system. Usually, people take I to the right and J up. You can take it any direction you want, but usually you want to be consistent with it so that you don't have to remember what you did for each of the particular ones. And then once you choose the I and the J, somewhat arbitrary, you have to determine what the K is. You use your right-hand rule, which we've talked about in class, to determine that in this case the K is going to be out of the page based on where you chose your I and your J. Okay, the next thing is for each of the bodies, determine the angular velocity. In this case, it's a simple angular velocity, so it's equal to a rate of change of an angle. So the rate of change is theta dot. Now I have to determine the direction. The way you do that is you say, all right, if theta dot is positive, that means theta is getting bigger. Now look at the picture. If theta is getting bigger, which way is the guy rotating? He is rotating clockwise. Take your right hand, curl your fingers in the clockwise direction. Your thumb is going to point into the page. Into the page is the opposite of K, so that's why it's a negative K. So that's the angular velocity. Now that you have all of the angular velocities, or equations for them, you simply write down your special point equation. Okay? Now, here's the special point equation right here, and you have to decide which point you're going to put on the left. It doesn't really matter, just pick one. So I chose B, so that's somewhat arbitrary. The other point goes on the right-hand side. So velocity of B equals velocity of A. The omega I've got from before, and then the R vector depends on where you put, what's on the left and what's on the right. It always goes from the subscript that's on the right-hand side of the equation to, and I'm going to draw it with an arrow so you know it's to. It goes from A to B. This variable here, B, has to always be the point that you put on the left-hand side. Now the VRELs, the way you find the VRELs is you actually imagine that you're standing on the link and you look at A and B. And if you look at A and B and they look like they're moving, then you would have a VREL term. In this case, if you're on the link, just like if you're on the earth and you're looking at a book on your desk, and the book is setting still on the desk, the book will not look like it's moving, but it is because it's on the Earth and the Earth is spinning. But what you see is nothing, and that's what the VREL term is. If the 2 points, if the 2 special points in this equation are fixed to the link, the VREL terms will all be 0. So they are in this case. So most of the time they're 0. Okay, so now I'm just going to plug numbers in. So the velocity of B. Well, the velocity of B is a speed that I don't know, little VB, but I do know that it's pointed down this incline. So I know it's headed down this direction. And so I put that in as a vector. So it's going a distance of cosine 30, and it's left. That's a negative I. And a distance is sine 30, and it's down, negative J. Okay, and then for the velocity of A. The velocity of A, the magnitude is 4.2, and it's going down, negative J. And then for the omega, I just plugged in the omega. So here's the omega. And then for the R is going to be a distance of 5. It's going 5 cosine of theta, and it's down, negative J. So I'm going from A to B. So I'm going to go down, and then I'm going to go left. And so that'll be 5 sine of theta is the distance, and left is a negative I. Okay, so that's how I plug in. Next thing to do is to take the cross products. And okay, I noticed I had made a mistake, so I paused it for a minute and fixed it. So anyway, what I'm doing here is I'm taking the right hand side. So I'm just focusing on the right hand side. So this piece right here is the right hand side of the equation, right? So I'm just copying it down. Now, to do the cross products, what I like to do is I like to pull out all of the constants first. So I'm going to pull out the 5. Right, there's a 5, and there's a theta dot common, and there's a negative sign on the theta dot. So I pull all that out. So I pull out a negative, the 5, and the theta dot. Pull that out. And now what I'm left with is K cross cosine theta J. Right? So again, I'm going to pull out the constants. So in the parentheses, I pull out a negative cosine theta, and now I need to do K cross J. I use this little diagram over here to do it, right? So you might want to make a copy of that. And the way I use it is I put my pen on the first vector and I move towards the second vector, ending up on the third vector. So for example, I want K cross J. So I start on K, I move to J, and I skip it and land on the answer of I. So K cross J is I. It's either plus or minus, right? So I have the negative that I copied down from the above, cosine theta I copied down from above, and then the K cross J is an I. So I got that from my diagram. Now, to get to the I, did I go in the positive direction in the blue arrow over here? Did I go in the positive direction? No, I went backwards to get to the I, so that's a negative. So K cross J is a minus I. So I have a minus from the equation above, and then the K cross J gives me another negative, so I get a negative, negative, makes a positive there. Okay, let's do now the next term, right? So I pull out the sign, I pull out the negative and the sign, and I'm left with K cross I. So now I'm going to do a K cross I. So I start with the first vector, K. I go towards the I, pass it up, and I end up on the J. So I end up on a J right here. Was I going in the positive direction or the negative direction? I was going in the positive direction. So K cross J is a K cross I is a positive J. So that doesn't change this negative sign, right? The negative came from copying from above. So that one remains that way. Okay. So now the next step, now that I've done the cross products, is I just pull off all of the I components. So this term right here is the I values of the left-hand side, right? V minus VB cosine of 30. And then on the right-hand side, that's all of the I pieces on the right-hand side. And I see I've made another sign mistake. So the only I component over here is this piece right here. And if you notice, I forgot another negative sign, so I'll put it in there. There we go. Okay. Then you pull off the J components. So here is a J component. Here's one, along with right there on the left-hand side. There's a J. So minus VB sine of 30. And then you pull off all the J's on the right-hand side. So here's a piece. Comes down to here. And then there's another piece right here. There's one. And there's one right there. So minus minus becomes a, again, I made another sign mistake. There you go. Plus. Negative negative is positive 5 sine theta, theta dot j. Okay, how many unknowns? 2. VB and theta dot. You had the same 2 up here, right? You notice there's a VB here before I did all the cross products and a theta dot up there. Okay? So anyway, and then 2 equations, 2 unknowns, and you solve it, which is doable. And then what I like to do is I like to use Mathematica to solve it. So I'm going to show you how to use Mathematica to do these. Okay, so this section right here is the file vector4. I think it's called vector4, vectors maybe, vector4.mb. And so that stuff is already typed in, so you can just open that file and have it. So here's the problem I'm doing. And what I like to do is, writing vectors gets a little ugly sometimes. So I like to separate it off, and I put them in up here. So based on the work that I have done in the previous file, I know that I need R and omega and things like that. So that's what I'm going to do is do that. All right. So I just like to, I hate to type degrees, so I'm going to define angle 30, A30 as 30 degrees. And I define a down the incline, because I know that that is the direction that B goes, down the incline. Down the incline is a vector this way. It points down the incline, right? Your I is over here, your J is up, if you remember, right? And then this would be down the incline, down incline. And down the incline is going to be a distance of cosine of 30 degrees, right? Left, so negative I, and it's going to be sine 30 degrees down, negative J. Okay? So that's my down the incline. Here's my velocity of A. Velocity of A is 4.2, and it's down. Right? Don't write it as 4.2 minus J. This is 4.2 times a negative J. Velocity of B, it's going to be the magnitude, VB, and it's down the incline. So that's the direction. The omega, I copied that off of the other. It's a minus theta dot K. Theta is 50 degrees. That was given in the problem. Down rod, this is what I'm going to use to get the R vector. So this is going to be a vector that points down the rod. So it's going to be like this. This is down rod. That direction is down rod. And that would be sine of theta this way, cosine theta that way, right? So that's going to be cosine theta down, negative J, and it's going to be sine theta left, minus I. So my R from A to B is the distance 5 down the rod. So that's my vector for that guy. And then here's my special point equations. Velocity B, 2 equal signs, because it's an equation, equals velocity of A, and then here's how you do a cross product. Cross omega with R. And then there is no VREL. Hit execute, and this is what you have. Notice with the commas, this guy is the I piece on the left-hand side. This is the J piece. The I piece is on the right-hand side is this piece, and the J is this piece right here. And the K's are obviously 0 because it's a two-dimensional problem. And then you want to solve the equation. So this guy has been defined at the top. That's why you want to include it. Right? This be solved right there. It's already there. I've defined it. And basically it solves a vector equation. And you want to solve for VB and theta dot. Then there's your two answers right there. Okay, that's it for this one.